time. We live by it, depend on it. Obsess ober Italiano. It governs our days, shapes our decisions, and defines our lives. But have you ever stopped to wonder, where did this idea come from? Is time real, or is it something we made up? What exactly is time, and how did we come to think about it the way we do? The concept of time as we understand it today is not fixed in nature. It is not an eternal truth. Instead, it is a human creation, shaped by our history, our beliefs, our inventions, and our need to bring order to a chaotic world. What we call time is a blend of science, philosophy, religion, and technology, woven together over thousands of years by countless cultures. In the beginning, time was the sky. Before there were clocks, before calendars, there were the stars, the moon, the sun. The sky was the original clock, and early humans looked up to mark the passing of days and seasons. The cycles of the heavens gave rhythm to life, a pattern of light and darkness, warmth and cold, death and rebirth. Some of the earliest formal timekeeping emerged in Mesopotamia, the land between the rivers, over 5,000 years ago. The Sumerians, masters of observation and mathematics, developed a basic 60-number system that still shapes how we divide time today. 60 seconds in a minute, 60 minutes in an hour, 360 degrees in a circle. For them, time was linear, a story that moved forward. They recorded eclipses, charted planetary motions, and began to track time not just for survival, but for prediction, using time to foresee omens, to schedule rituals, and to maintain cosmic order. While Mesopotamia gave us structure, ancient Egypt offered a different lens, one of eternal cycles. The Egyptians divided their day into 12 hours of daylight and 12 of darkness, not based on clocks, but on the natural rhythm of the sun. Time to them was cyclical. Life, death, rebirth, mirrored in the flooding of the Nile, the rising of the sun, the journey of the soul. Their concepts of time, Nye, the repeating time of the cosmos, and Jet, the eternal time of the gods, framed a worldview where the past was never gone, only returning. Every sunrise was a recreation of the first sunrise. Every year, a sacred return. To the east, ancient China developed its own intricate relationship with time. The Chinese calendar was lunisolar, balancing the moon's cycles with the sun's path to track the seasons. Their philosophy, rooted in Taoism, Confucianism, and later Buddhist influences, saw time not as a straight line or a single circle, but as a dance of balance. The concepts of yin and yang reflected opposing forces cycling through seasons, years, and generations. Time was harmony. To live well was to move with the grain of time, to plant, to rest, to govern, all in accordance with cosmic rhythms. And yet, in Mesoamerica, the Maya civilization brought forth one of the most advanced and profound systems of time the world has ever known. The Maya believed time was both cyclical and linear. They tracked sacred days in the Tucan calendar, seasons in the Hab, and massive cycles of creation and destruction in the long count. Time was alive, every day a spirit, every number a force. Their calendars were mathematical, mystical, and massive in scale, stretching thousands of years forward and back. The end of one cycle wasn't the end of the world, but a transition, a reset, a breath before the next beginning. In ancient Greece, time took on philosophical dimensions. The Greeks had multiple words for time. Chronos, the relentless, linear time that devours all things. Kairos, the opportune moment, the right time to act. And Ayen, the eternal time, the great age. Time wasn't just measured, it was contemplated. Plato saw time as the moving image of eternity. Aristotle called it the number of movement, in respect of before and after. For the Greeks, time was not just what the sun did, it was what the mind perceived. The Islamic Golden Age brought with it both reverence and innovation. The Quran speaks of time as God's domain, reminding humanity of life's fleeting nature and the urgency of virtue. The Islamic calendar was purely lunar, circling through the seasons, untied from solar correction. Yet at the same time, Muslim scholars built some of the most sophisticated timekeeping devices of the medieval world: water clocks, astronomical tables, mechanical automata. Engineers like Al-Jazari designed intricate machines that measured time, chimed the hours, and displayed cosmic motion. Time was both sacred and scientific, a divine rhythm, and a challenge to understand. In medieval Christian Europe, time was holy and hierarchical. The day was divided not by hours on a dial, but by prayers, matins, lauds, prime, terce, sext, none, vespers, and compline. Monasteries ran like clockwork, before clocks even existed. But in the 13th and 14th centuries, a quiet revolution began. The invention of mechanical clocks, these early machines, driven by falling weights and escapement gears, did something radical. They divided time into equal, unchanging hours. No longer did hours stretch and shrink with the seasons. Now, the hour was a constant, and with that time began to tick independently from the sun. This mechanical view of time changed everything. Clocks spread through cathedrals, town squares, and eventually into homes. The day no longer belonged to nature. It belonged to the bell. Work was measured. Sleep was scheduled. Life became punctual. The idea of wasting time was born. Time, once sacred and shared, became private and economic, a resource to spend, to save, to manage. By the 17th century, the pendulum transformed clocks into precision instruments. Galileo first studied the pendulum's swing, but it was Christian Huygens who built the first pendulum clock. Suddenly, clocks were not just close, they were accurate. The hour was no longer good enough. Now the second mattered. And with accuracy came ambition. Sailors sought to navigate by time. Scientists began to think of time as a universal constant, a grid on which the laws of nature operated. Enter Isaac Newton. In his view, time was absolute. It flowed uniformly, like an invisible river, unaffected by anything. It was the backdrop to motion, the ruler of cause and effect. Newton's time was mathematical, objective, and universal. Every clock in the universe, if perfect, would tick in harmony. But nature, it turned out, had other ideas. In 1905, Albert Einstein shattered the illusion of absolute time. His theory of special relativity showed that time is not fixed. It stretches and contracts depending on your speed. A moving clock ticks slower. A twin traveling near the speed of light will age more slowly than the one who stays behind. Time is not the same for everyone, e.d.s relative. Then, in general relativity, Einstein revealed that gravity itself bends time. A clock on a mountaintop ticks faster than one at sea level. The stronger the gravity, the slower the time. Time had become part of the fabric of the universe, not separate from space, but intertwined, what we call space-time can curve, twist and ripple. And still, science wasn't done with time. In quantum mechanics, time is a strange guest, present but elusive. The equations that govern particles work equally well forward and backward in time. There is no built-in direction, yet in our experience, time always flows one way, from past to future. Why? The answer lies in entropy, the tendency of systems to move from order to disorder. This is the arrow of time. It's not written into the laws. It emerges from the conditions of the universe itself. A cup falls and shatters, but shards don't leap back into a cup. Time's arrow points forward because the universe began in a state of low entropy, a cosmic egg from which disorder would endlessly increase. While philosophers and physicists debated time's essence, engineers were still refining its measurement. The 18th and 19th centuries brought portable watchers, accurate chronometers, and eventually the industrial clock that ruled factories, schools, and cities. Time became synchronized across entire nations. But there was a problem. Before the 19th century, every town used local solar time. Noon was when the sun was overhead, and it was different everywhere. That worked fine when travel was slow. But railroads and telegraphs changed everything. Suddenly, trains needed timetables, and people needed to know what time it was, not just in their town, but in another. Hundreds of local times created chaos. So, in 1883, North American railroads imposed standard time zones. The following year, at an international conference in Washington, D.C., the world agreed to adopt Greenwich, England, as the prime meridian, the 0.4 global time. The planet was divided into 24 time zones, each 1 hour apart. And just like that, time became global. Noon no longer meant the sun overhead. It meant whatever the standard said it meant. A town's clocks might be 17 minutes ahead of the sun, and no one cared. Time had become coordinated, agreed upon, defined by law. It was now a convention, not a cosmic truth, but a human decision. The 20th century took precision further. In 1927, the first quartz clock was built, vibrating at thousands of times per second and keeping time with astonishing accuracy. But even quartz would be surpassed. In 1955, the first cesium atomic clock was unveiled. Atomic clocks measure time not by motion, but by the frequency of atomic transitions. The natural vibrations of cesium atoms, so regular are these ticks that a modern atomic clock would lose only 1 second in millions of years. In 1967, the second itself was redefined, no longer based on the Earth's rotation, but on the oscillation of a cesium atom. Time was no longer tied to the heavens. It was rooted in the heart of matter. Today, atomic clocks underpin everything. GPS, satellites, internet synchronization, financial systems, even power grids. And to keep civil time aligned with the Earth's slow and irregular spin, we sometimes insert leap seconds into coordinated universal time. Even now, we must negotiate between cosmic time and human time. And yet, the future may hold even stranger shifts. Quantum physicists speculate that time itself may be emergent, not fundamental, but arising from more basic relations. Some theories suggest time may not exist at the deepest level of reality. In others, time could be an illusion, a trick of consciousness riding the entropy wave. Even in cutting-edge technology, experiments with optical lattice clocks now measure time so precisely they can detect the difference in time between your head and your feet. Through all this, time remains a mystery and a mirror. It reflects who we are. In ancient times, time was sacred, cyclical, cosmic. In the industrial age, it became mechanical, regimented, a currency in the scientific age. It became flexible, strange, and deeply entwined with the universe itself. But always, it has been ours. Time is a human story, a way of making sense of change, of ordering memory, of marking our place in the cosmos. We built it, named it, sliced it, and now we measure it to billionths of a second. And yet, no matter how precisely we track it, we can't hold it. It slips forward. 1 second, then another, and another. In the United States, Congress made the Railroad Zones Law with the Standard Time Act of 1980, which also established daylight saving time seasonal clock shifts during WWI. Beat at point the 4 continental U.S. zones, plus additional zones for Alaska, Hawaii, etc., were well accepted around the world. Many countries aligned their standard times to convening meridians or adopted half-hour or quarter-hour offsets to better match local solar time or political boundaries. For example, all of China today uses a single time UTC plus 8, even though geographically it spans 5 ideal time zones. Some countries, like India, UTC plus 530, and Nepal UTC plus 545, use half-quarter-hour offsets to fine-tune their zone. The implementation of time zones was one of the great standardizations of the industrial age. It transformed time from a local property, different in each town, to a global grid where everyone could refer to a single universal reference. Communications and travel were made far more efficient. A person could confidently schedule a telephone call across continents, knowing exactly what time it would be on the other end, once both agreed on GMT or its successor. Indeed, coordinating time globally became crucial with the advent of radio and international telegraph. Time signals were broadcast over radio starting in the 1920s, allowing ships at sea or remote locations to tune in and set their clocks accurately. This was essential for navigation and scientific observations like timing, eclipses, or celestial events, simultaneously from different countries. In the mid-20th century, the basis of the world's timekeeping shifted from Earth's rotation, which defines G based on the mean solar time at Greenwich, to atomic clocks. As mentioned earlier, atomic clocks in the 1950s-60s outperformed astronomical time in stability. However, Earth's rotation is not perfectly uniform. It slows down very slightly and irregularly by a few milliseconds per day over years. Due to tidal friction and other factors, by the 1960s, using the Earth's rotation as the definition of the second and thus of time zones was causing discrepancies between atomic time and astronomical time. To reconcile this, a new timescale was introduced, Coordinated Universal Time (UTC), in 1972. UTC is based on the output of atomic clocks, so it ticks uniformly, but it is occasionally adjusted by 1-second increments. Leap seconds. To stay within 0.9 seconds of UT1, which is essentially Earth rotation time. In practice, this means that the world's official clocks run on atomic time, but every year or two, a leap second is inserted, usually on June 30th or December 31. To ensure that civil time remains synced with the position of the sun, so that noon is still basically when the sun is overhead at the reference meridian. This compromise maintains a connection to the traditional concept of solar time while leveraging the stability of atomic clocks. UTC replaced GMT as the International Standard Time reference in most technical and legal contexts. For example, time zones today are often stated as offsets from UTC, not GMT, though in casual use they coincide to within a second. Organizations like the International Bureau of Weights and Measures, BIPMA in Paris, coordinate time by collecting data from atomic clocks in over 70 labs worldwide to compute international atomic time, from which UTC is derived. Thus, the global coordination of time is now a highly scientific enterprise. Signals from GPS satellites, Internet time servers, and national metrology institutes all disseminate precise UTC, ensuring that, say, when it is 12 o'clock UTC in London, every other time zone can compute their local time to the exact second. In summary, the invention of time zones created a standardized world timetable out of local solar times, an innovation driven by the needs of modern transportation and communication. It involved adopting Greenwich as longitude 0, and carving the globe into 24 slices of 15, each with many local modifications for political boundaries. Over time, refinements like daylight saving time, seasonal shifts, usually of +1 hour in summer, first widely adopted during WWI, were introduced in some regions to make better use of daylight in higher latitudes. Today, time zones are a taken-for-granted part of life, but their implementation was one of the key steps in the globalization of time, putting the whole planet on the same temporal page. Time, in the end, is the story we tell of where we are, where we've been, and where we hope to go.